Students, in this video we will discuss about the EMF equation of a transformer. Here we have considered one transformer which is having a primary winding as number of turns N1. On the secondary side, number of turns are N2. The primary winding is connected to the voltage source V1, whereas the secondary winding having a terminal voltage as V2. E1 is the self-induced EMF in the primary winding, which is due to the flux phi set up in the primary winding when there is a flow of current I in the primary winding. Then E2 is the mutually induced EMF in the secondary winding because of this phi. Okay, so this phi is what it is, a magnetic flux, and the nature of magnetic flux, as we know that this phi is set up because of this current which is flowing in the winding. Okay, so the nature of this current is sinusoidal, therefore the nature of the magnetic flux is also sinusoidal. So we have considered one waveform over here. This is the sinusoidal waveform of a magnetic flux. Here one cycle is considered for a AC cycle, AC waveform. Suppose T is the time required to complete one cycle, and T is what it is, a time period. This time period is given by 1 upon F, where F is what it is, a frequency. So the full time to complete one cycle is capital T. So how much time it will take to complete half of cycle? It is T by 2. Then how much time is required to complete 1 quarter or to attain the maximum value of flux phi? And here we can say this is what phi m. So how much time it will take to increase from 0 to maximum? It will T by 4 seconds. Okay, so we can write that this is what this x-axis is, time axis, and y-axis is what, magnetic flux axis. Therefore let N1 is what, number of turns in primary side, primary winding. Okay, this is what the primary winding, number of turns are N1. Similarly N2 is what, number of turns in secondary winding. Phi m is what, it is a maximum flux in the core, and this is what, this value is what, this when phi increases from 0 to and attain its maximum value, suppose it at A, this is what the, at this point maximum flux will occur in the core. Therefore phi m can be given as Bm into A, where Bm is what, it is maximum flux density in Weber per meter square, and A is what, it is a cross sectional area of core in meter square. T is what, T is a time period in seconds, and F is what, frequency of AC input, and F is what, it is 1 upon time period, or we can say that time period is what, it is 1 upon F. Okay, now one thing is very important. As per Faraday's law, we have to remember or keep in mind the Faraday's law. Faraday's law, what does it says? Whenever a conductor cuts magnetic line of forces, it induces an EMF. Means E is directly proportional to d phi by dt. D phi by dt is what? It is the rate of change of flux. Okay, means the fluxes keep on changing, and if the fluxes keep on changing and it is and it cuts the conductor, then what will happen? There is a production of EMF. Therefore we can say E is equal to N d phi by dt. This equation we have to keep in mind. Okay, so now what would happen? How much time it is taking from 0 to maximum value? It is taking 1 by 4. So we can write that flux increases from its 0 value to maximum value in 1 by 4 seconds. Suppose we are taking T is as 1. So how much time it will take? 1 by 4 seconds. So we have written flux increases from 0 value to maximum value in 1 by 4 seconds. Next is average rate of change of flux. Now the flux is changing. When the flux is changing, it means it is changing with respect to time. So we can say that phi m divided by with respect to time, and time is what? It is 1 by 4. So we can write that t by 4. In this much time, how much flux is attained? It's attaining the maximum value. So we can write phi m divided by t by 4, which could be written as phi m divided by 1 upon 4f, as t is equal to what? T is equal to 1 by f. So we can write like this. Okay. Now this rate of change of flux per turn means induced EMF in volts. As we know that E is equal to n d phi by dt. It means E divided by n is equal to d phi by dt, and E divided by n is what? EMF per turn, or we can say that it is induced EMF. So we can write that E, or average EMF per turn is equal to, we can write phi m divided by 1 by 4f, or we can write it as 4f phi m. Okay. Now next is for an AC quantity, means phi is varying sinusoidally. So really, it means it is varying sinusoidally, means it is a AC quantity. We can consider a factor known as form factor. Therefore form factor is given as form factor is equal to RMS value divided by average value, and for AC quantity the form factor is 1.11. okay, therefore we can say that RMS value is equal to 1.11 into average value. And average value, we have just derived an equation for that. That was average EMF. We have derived an equation that average EMF per turn is equal to 4f phi m. So we can consider this, and we can write average EMF per turn is equal to 4f phi m. Therefore we can write average EMF is equal to 4f phi m into turns, and this turn is what could be written as 4f phi m n1 if we are considering the primary side. So keeping this value of average value in this equation, therefore RMS value, whose RMS value? It is E, or induced EMF RMS value, is equal to 1.11 into average. E average is what? This is 4 into f into phi m into n1. So we can write that, and this is what, if we are taking it as a n1, so this is what E RMS 1 means RMS value at primary side or primary winding, for primary winding. Therefore we can write it as E1 is equal to 4.44 into f phi m n1. Okay, this is what the EMF equation for a transformer referred to or towards primary side. Or similarly we can write it as similarly E2 is equal to 4.44 f phi m n2. This is what induced EMF in primary side equation. So we can write E1 like this and E2 is like this. This is what basically the EMF equation for a transformer. This can also be written as E1 is equal to 4.44 f. Instead of phi m we can write bm A N1. Similarly, E2 is equal to 4.44 F BM A N2. Okay, this is what the EMF equation for a transformer. Okay, thank you.